Hi, everybody. My name is Bridget Murphy from University of Kiel and from DAISY in Hamburg. And I would like to tell you about doing experiments at large-scale facilities and how to make your data fair and open, how to use best practices and workflows in X-ray and neutron science. The topic of this paper is fair data. The photon and neutron communities move together towards open science. You can see here the authors are Bridget Murphy, Andy Gutz, Christian Good, Cormac McGuinness, Henning Ronno, Astrid Schneiderwind, Stefan de Rade, and Ulrich Pietsch. And not only these, but also contributions from all of the European Synchrotron Users Organization and ENSA, the European Neutron Alliance. The focus of this paper was made at a meeting of USO and ENSA and Daphne for NFDI meeting in PSE in November 13 to 15, 2023. And what is Daphne for NFDI? Daphne for NFDI is data for photon and neutron experiments. And I'm the speaker of Daphne for NFDI. And in Daphne, we are really passionate about making data fair, making better science possible by providing high quality digital data so that people can use it and reuse it. And in November 23, we came together, the user communities, together with Daphne, and developed a white paper on the importance of fair and open data principles, and to crystallize the user's perspective on how users and research infrastructures can work together to fill their common accountability. We came together with the user communities and developed a white paper on the importance of fair and open data principles and to crystallize the user's perspective on how users and research infrastructures can work together to fulfill their common accountability. So if we think about fair data, as I mentioned before, what is fair data? I'll tell you in a minute, just hang on. We want to talk about research data management. We want to talk about roles and responsibilities of the large-scale facilities, or here as we refer to them, research infrastructures, and users, in this case, scientists who come to do experiments at the research infrastructures, about shared accountability and workflows and best practice procedures. We want to think about the current status in science, how to come and make best practice sustainable, to provide opportunities for transformations, and that's also as part of Daphne, and then I will give you some examples. So what is fair data? I hope that everybody knows what fair data is, but just in case, fair data is data that is findable, accessible, interoperable, and reusable. So if the data is findable, it needs to be well indexed. And this, we talk about metadata. This is something that's assigned to describe your data file. You can think of it like the name. When you want to go to the library and find a book, you don't see the whole book. You just find the author and the publisher. Metadata is this similar kind of information that's key to help you find the file where the full data set is. Also, the metadata should be clearly and explicitly included in identifiers. These identifiers need to be persistent. This means that if you make a link to your data, it has to last for a long time, forever, maybe. And metadata can be registered in a very clear indexed form. And depending on what community you're in, then you use a particular standards of metadata so that other people can also find your data. So now if we've decided how we can make the data findable by describing it clearly, who created the data, where was it made, what kind of sample are you investigating, what kind of an experiment did you do, how many data points did you measure? Now you have your metadata, and now we want to come and make it accessible. And so if it's accessible, you need to have a standard protocol to get to it. This means that this protocol has to be open, free, and universal. It cannot be some private software. The protocol needs to allow to authentify and authorize, if required, to say who wants to look at the data and do they have the permission to look at it. And the metadata should be accessible even if the data is not accessible. So then you can find out from the metadata who was the author, and then you can contact them for more details. And interoperable, so now you've made your data findable and somebody can get to it. Interoperable is the next challenge. And this is making sure that it's reused, that it's platform independent. So you use a formal, accessible, shared, and a broadly applicable language. You use dedicated vocabularies that follow the FAIR principles, and also the metadata should include quantified references to other metadata. So that sounds very strange. What does that mean? So for example, if your metadata is describing an experiment, and in that experiment, a particular software or a particular sample was used, then to make it interoperable, you also have to provide the metadata for the sample and the software. Reusable. So now you've found it, you can get to it, you want to be able to reuse it. So this means that the metadata needs to be rich enough to describe accuracy and relevant attributes to the data set. They should be released with a clear and accessible data usage license so that the permissions are there for people to use it. It also needs to be really well associated with the provenance. In other words, who prepared the sample, who carried out the experiment, who wrote the software. This is, of course, to allow scientific acknowledgement for people who've put a lot of hard work into preparing these things. And the metadata also needs to meet community standards. So the FAIR data principles provide benefits and risks to the community. So I present you, first of all, the benefits, which include better science, ease of data handling. Of course, the first person who benefits is yourself, because you can find your data, and your group, because they can find it. And even maybe when somebody's finished their PhD, the group can still reuse the data afterwards. And outside the group, across a large collaboration, not just the people in the group, but also outside the group can refer to data. For example, maybe nice reference data sets that have been collected on previous experiments, and you want to reuse them to see if a new experiment is going well. And then the furthest aim, sharing the data with other scientists across the world. Also, it means that the data can be reanalyzed. So if there's some new development in the software or some new theory and the data is well describable, then you can check new theories with old data. And it makes it sustainable. So can the data survive when the master student is finished, when the PhD student is finished, when a postdoc moves on to a professorship or to a position in industry? This is a way of making the data long livable. And we really want to lower the tools, because lower barriers. We really want to lower barriers for reuse by others. And to do this, we provide tools. These tools need clear documentation. They need to be available and they rely on the availability of the data and the analysis tools. And also some machine learning and digital twinning can be extremely useful to this end. Another addition would be that by providing all the data available and reusable, then people who don't have access directly to a photon and neutron research infrastructure, PAN-RI, could also benefit and use the data or practice before they come for a beam time to go through analysis steps and workflows. Of course, such a big, brave achievement would also have risks and challenges. And some of these are limited effectiveness. Why? Because of limited resources, And if we don't have enough resources and enough cooperation across the community, it's very hard to actually achieve the fair data principles. And so this is why these risks need to be mitigated through the cooperation across the communities and research infrastructures. And this requires funding, requires a financial basis for the development and maintenance of the tools, as well as for data storage and curation. I think we would think, and you too, I hope you can convince you that the benefits outweigh the risks. So what would a research data management strategy look like? So in the community where you're using large-scale facilities, your experiment would start with writing a proposal. So the scientific quality of the experiment is already measured, assessed by peer review before you come to the experiment. And then when you get to the synchrotron or free-electron laser or neutron source, the first thing you're dealing with is how to collect your data. And if you want to make your data fair, you need to think of capturing the metadata, of course, the data, and this should have a common data format, for example, Nexus. You need to look at the control software and the metadata, high quality metadata, so that people can find it. You have to document the process of your experiment, noting down the workflows, using an electronic logbook, and in that discussing the details and the reasons why you choose to do the measurements, and also recording the measurements themselves. This leads us on to the parameters. So you would, of course, expect to have the parameters of the instrument, and usually your local large-scale facility will look after this for you. But for fair data, we also need to collect all the parameters related to the sample and to the sample environment, which may be from the users or from the facility. Now, once you get your data, or during the experiment, it's very important to be able to visualize the data online with live viewing, to be able to reduce it and validate it and process the data and then analyze the data. And these steps of evaluation are key to getting published papers, but it's also some steps that are not often published within the paper. So publishing how you do your analysis, how you integrated the data, how you validated, all these aspects are related also to fair data. And of course, from the start, from you get your very first scan, you want to be able to store it. And also the process data wants to be stored, and the fully analyzed data. And for people to be able to reuse the data that you gathered in your experiment, this needs to be curated. So the data that's stored needs to be validated, needs to be stored and archived, including both the metadata and the data. And if people are to access it, it needs to be in a data catalog so that we can share the data. And this catalog needs to be either access controlled or have access, open access. So if we have all these aspects, then we have a data catalog that is federated, searchable, interlinked, and this helps us to make the data reusable. And of course, then at the end, when you publish your paper, then you would expect not just to have a paper as the normal form, you would also expect some information on the sample, some detailed explanation of the software analysis and workflow, and also a data publication, including the data that you measured as well. So if we consider the roles and responsibilities of the research infrastructures are a central point of contact to the users. This is where they come to do their experiment. And therefore, they can motivate, inform, and transfer knowledge on skills on fair data practices to the users. So how does this work in practice? Really, when people get to the synchrotron, we can illustrate the best practices in data handling, can train the users on the use of the most modern tools and applications, can have a good data policy and explain how the data policy follows the FAIR principles, and discuss it and update it together with the user community, considering the following aspects: the acquisition and storage of the raw data and metadata during experiments, the reduction of raw data, the accessibility to data, and data security and embargo times. An embargo time is a certain length of time after the data has been collected where it's available only to the group who applied for the beam time. Also, we need to provide tools and workflows because at the moment there aren't not so many which allow people to follow FAIR principles. And considering this would be the tools that could be provided by the research facilities are capturing the data and the metadata, an electronic logbook, and a metadata catalog. And to make the data interoperable, it's very important to use common file and metadata formats. If we do this, then this leads us on to sustainability. And this is really a very important aspect of the role of the research infrastructures because they have the resources and the continuity in staff to provide sustainability. Now, on the other hand, we also have to think about the role and the responsibilities of the users because they come and they interact at the research infrastructures and they also react among themselves. And we know that the research infrastructures are a central point. So we have to, the research infrastructures can inform the users about the best scientific practice and lead the way by providing the necessary tools for implementation. However, the scientific useful implementation of the FAIR principles needs strong engagement from the users in the process of design, preparation, execution, and an experiment at the photon and neutron facilities. And to do this, we need to create a common set of standards within the community to provide domain-specific metadata. So what do we mean by domain-specific metadata? This, if you're doing EXAFs, or if you're doing diffraction, or if you're doing neutron time of flight, depending on your community will have some very specific metadata that's important to be able to find and reuse the data. It's important to provide tools required for FAIR data research data lifecycle. For example, users are also required and should provide and share the tools that they develop for software. Engage with the facility and provide accurate information in their experimental proposals and experimental reports. This means taking care to describe carefully what and why you want to do your experiment. Performing experiments, of course, with the help of the instrumental scientists, and ensuring the scientific quality of the data. So curation is really important for data that's reusable, and who knows better what the quality of the data is than the scientist who carries out the experiment. It's also important that users provide access information on sample, workflow, data reduction, and data analysis, as we mentioned previously, and provide comprehensive metadata. And then the publication that comes after all of that should follow open data best scientific practice. For example, the sample, the data, and the analyzed data should also be represented by a digital object identifier. Now, that's all very general, so let me give you a particular example. So we have a soft matter reflectivity use case, which is a collaboration between Kiel and Thüringer and DAISY. And here you can think of this as the workflow. We have a sample, we do an experiment, we collect some raw data, we extract a data set from it, and then we fit and model that data, and hopefully at the end there's a publication. So how do we make this fair? First of all, when we get the sample, we record the details about the sample metadata using ISGN. This is a persistent identifier that allows you to record details about your sample. Then we take it to the synchrotron, and when we there collect the data, first of all, the raw data and metadata is collected by the facility, but we keep an electronic notebook for full documentation of the experiment. You can look at this if you look at this reference here. This is how to make a good electronic laboratory notebook that works at large-scale facilities. When the data is collected at the beam time. This should be in a common format, for example, Nexus, and the data need to be saved into a repository that can be made open later. And in the metadata catalog, we use the SciCat catalog, which is a collaboration across Europe. Not only do we need the metadata for the raw data that's collected, but also for the extracted data. And we would like to now fit the data, and it's important to keep the software also in a repository. In fact, we have developed software to quite a high level in collaboration with the Thüringer group. And we carried out an experiment at the ESRF where we used closed loop feedback using artificial intelligence and machine learning tools so that we could do direct feedback through a measurement. And if you're interested in this, you can look here at this reference. So once we fitted the data, and now we also want to put this fitted data into an open data repository. And for this, we can use the public-data.desi.de, which provides a data bank for X-ray and neutron reflectivity data, and also for other methods. And then, if we've done all this very carefully, then we will have a publication, and we refer in the publication not only to the data, to the repository, but also to the raw data and to the software that was used to analyze it. And back, of course, to the very start, to the sample description. You can see an example of how to do a fair data paper in this example by Sonja Hübelmann in the IUCRJ. So this is one working example, but to make things work, not only do we need working examples, but we also have to work together. So we want to consider the shared accountability and workflows and best practice procedures between the users and the research facilities, and how to achieve a fair data scheme. This is important to have a good experimental conception, to describe your sample preparation, the conduction of the experiment, and the data analysis to interpret for the interpretation and publication of a scientific paper in a peer-reviewed journal. It's also important to define the metadata standards, deciding which information, such as the metadata workflow, the data, the sample persistent identifier, or PID, and the software digital object identifier. You need to check out and monitor the procedures that you're using for fair data and work on further improvements together, both the users and the facilities. You need a bilateral involvement because this process really needs to be agile, and the development needs to be reviewed and changed regularly. We also want to ensure together that good or best scientific practices are continually followed and reviewed. If we do this together, we can also save resources. We should also have a good dialogue to decide which data should be kept. This is part of curation. If we know that data are not good, they don't need to be stored, and also whether we store them in a live form or on tape, and for how long. Now, the current status of fair and open data at the PAN facilities, and how do we meet the challenge? So the European Open Science aims to provide fair data, providing data, software, and services. And the Photon and Neutron Open Science Cloud, PANOSC, which ran from 18 to 22, the EOSC Photon and Neutron Data Service, or EXPANS, which ran until 23. And now the follower up from that, which is called OSCARS, and also provide necessary software policies and legal administration for frameworks for sharing data. We can enable open science through the adoption of FAIR principles and make the data open and fair and available to the EOSC. Doing this, another challenge is really the data curation. So the photon and neutron research infrastructures in the process of adopting the PANOSC FAIR research data policy framework consider the following aspects as key: metadata from raw data, data management plans, data catalogs, and a common protocol for harvesting data and metadata, data standards, for example, Nexus, e-learning platforms, and training. And what is the current status for the photon and neutron users? The PANOSC and EXPANS projects have expired, and now we have OSCARs. LEAPS have proposed a roadmap to continue the work started in PANOSC and EXPANS. And the true implementation needs to be realized between the individual facilities, considering national conditions. Users should give a clear signal that they want to have equal and good opportunities at all PAN facilities. And as I mentioned now a couple of times, the EU funding of EOS projects continues through the OSCARs project, which also gives the facilities the opportunity to work towards fair data. In Germany, the Daphne for NFDI consortia is financed through the Deutsche Forschungsgemeinschaft. And this is aimed at creating comprehensive infrastructure and tools to provide research data from photon and neutron research infrastructures according to FAIR principles. Daphne brings together the users across these facilities, representing key scientific application domains within the research infrastructures. So what is Daphne? Daphne is part of the German NFDE, National Federation for Data Infrastructure Consortia. This complies a vision across humanities and social science, life science, natural science, and engineering sciences. And here is Daphne here as part of the physical sciences. And the Daphne community impacts really on global challenges. So Daphne brings together the photon and the neutron communities, collecting high quality data using imaging, tomography, diffraction, and spectroscopy across research domains, including engineering, bioscience, physics, chemistry, and medicine. And through this data and experiments, we can impact on societal challenges across health, environment, energy, materials, transport, and knowledge. Daphne does this by focusing on the common needs and challenges, helping people from collecting their data management and data analysis to publishing papers using the FAIR principles. So now you have an idea of the tools, and I can tell you we're hoping to have EOSC nodes or more facilities from our community in the near future. How can we make sustainability and reduce the carbon footprint of FAIR data? In other words, how do we manage the resources at the large-scale infrastructures? So FAIR data helps to reduce the carbon footprint of science by avoiding redoing of experiments and optimizing the reuse of existing data. It helps us to reduce energy consumption. The data storage needs to be a compromise between storing all the raw data or only processed data or chosen data. This is a thing we have to consider, how to optimize and what's the playoff between availability and sustainability, and also to the balance between cloud storage and cold storage. So a possible long-term solution would be the establishment of a common data repository for PANs. And if this was set up in consultation with the users and the RIs, it would have several benefits. It would optimize the technology of data storage. It would standardize data and metadata formats. It would distribute the cost and the burden of data archiving across Europe. It would reduce the running cost and the carbon footprint of data archiving, and it would provide a single entry point for the users. And this is what I mentioned when I say we're applying for EOSC nodes, and this is going on at the moment. Also in Germany, we are hoping to have a national node, and this is run together between EOSC Beyond. So what are the opportunities for transforming within the user communities and the perspectives for users and the research facilities? So introducing and implementing this transformation to fair and open data will help increase transparency within our scientific discipline. It will help to increase exchange and discussion by sharing data and workflows across the scientific disciplines. It will provide new possibilities to share results and allow collaboration and far beyond. Also, it will allow data reuse long after publications and allow eventual new interpretations to follow. For example, review of the SARS-CoV data in Cameron et al. In 2023, or the more recent AlphaFold publications. These benefits, however, can only become a reality if a large number of photon and neutron users and the research infrastructures are convinced to follow fair research data management. So in summary, implementation of application of fair data principles is a big step towards open science. Because research at PAN facilities is financed by public money and the results of the research are not private but belong to the public. The users' organizations, USO, ENSA, and Daphne will give maximum support. So bringing this together, I'd like to thank you for your attention, and I hope that you have fun at the synchrotrons and you can appreciate the power of synchrotrons, neutron sources, and free electron lasers around the world. And maybe, who knows, maybe we see each other there. Thank you.